Okay, let's talk a bit about friction and what we learned the last 2-3 days on it, and what was in the reading here. First question asks, in what direction does kinetic friction act on a moving object? So if we have a now I already tried to fix this, and this is on video. It's just embarrassing.
I think we'll have a fire drill today.
Did
Last
it?
time you recorded, we had a fire drill.
Okay. So we have our this is fun. We have our moving object here, and let's say that it's moving in that direction, so it's got a velocity. What direction does kinetic friction act on it? Opposite direction of its motion. So there's some language in here, and I tried to make notes on people's readings. There's some language to refine when we're talking about friction. So one part of that is it's not necessarily the opposite direction of force that's being applied, but it is always the opposite direction of motion. Right? So you could say I could have a force this way that's causing it to accelerate that way. Friction would still be against me. Or this could be something that's already moving and I'm trying to stop it by pushing it this way, which could mean that the acceleration is to the left, but as long as motion is still to the right, friction is opposite it. So it doesn't tell us what direction directly the acceleration would be. We'll do one or two quick examples about different ways to look at this before we go into the homework type thing, or work time. But this is telling us the direction, it's opposite the direction of motion. The next one here, in what direction does static friction act on an object? What about static friction?
Straight down.
It is not straight down. The opposite way the force is, I think you're picturing it correctly, although that's one of those refinements that I want to make.
The opposite direction of the object would.
Right. So if there's a net force acting on something that would make it move in a direction, static friction will go the opposite way. So let's say that we've got no motion now because it's static. Static means not moving. But if I'm pushing in that direction, now it's opposite that force. So this would be a static friction that way. If I were pushing on, and if I had two people pushing, and they were different forces, let's say F push 2 is greater than F push 1, well, then it would tend to move towards the left. Static friction would act against the greater of the forces. But, as it says here, why isn't static friction a constant amount?
It only gets this large as the force.
Right. It can't get larger and overbalance a force. Because then it would, if we did this and this was, say, 2 newtons, this was 1 newton, the two of them, there'd be a net 1 newton to the right. Well, if static friction is 2 newtons, well, then we've got more force pushing that way, and static friction would actually make it move. And that can't happen. It can only be as large as whatever other forces, as Noah said. So it would only be 1 newton to keep things still. And that's why it's not constant. What we're going to be able to calculate is the maximum amount of static friction, but the actual amount really depends on the other forces acting on it, and it will never be more than that. It's a lot like a normal force. A normal force is typically, it can only be the same amount as the force pushing down. There are some exceptions to that one, but it's not going to be responsible for throwing something away from the surface. The surface could move with it. Think of an elevator going up. The surface, the normal force is greater than the gravity pushing down, but not enough to throw the object. And then the last one here, consider that an object that starts sliding, so like our lab. Which is larger, the static or kinetic friction? In this we had answers all over the place for this. What do you think is larger, static or kinetic friction? So let's draw a line. We're going to put a box on here. Hold it at some angle theta. And as we tilt this up, at some point, this box is going to start sliding. So my question is, which is bigger, static friction or kinetic friction, and how do we know?
Kinetic is greater because the object is moving. If the static was more than the kinetic, then it would.
Let's examine that. So Chrissy said that if static was bigger, then it wouldn't move. Right? So static friction is going up, 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 up until it reaches a breaking point, right? And then the two surfaces can't hold each other anymore. Let's say that kinetic friction is bigger than that. So it starts sliding, but kinetic friction is bigger than the static. So now suddenly it's got more friction than it used to, pushing back. What happens to it? It stops. Or slows down, but it only just started moving. So it would stop again if kinetic friction is bigger. So your reasoning was good, except you got to reverse it. Static friction must be the bigger one. So if this is friction, it would go up and then go back down to a constant kinetic friction. So here's Fs. It's climbing until it gets to the point where it breaks. And then kinetic friction has to be less, because otherwise that block would just stop. And then you'd be back in the static friction realm. That doesn't happen. Once this is broken, it's going to keep sliding, albeit slowly, because the kinetic friction is a little bit less. This right here is the reason that car manufacturers developed anti-lock braking systems. You guys know what that is? It's actually becoming more and more important now as we go into winter.
It's where if the steering wheel can't steer, the brakes start breaking off and on really fast.
It's not a steering thing. It's a braking thing. It's if you slam. It used to be if you slammed on the brakes would lock in a car, and this could happen on pavement or but most especially on ice. And when it locks, the wheels don't turn. So the force trying to stop the car is all this kinetic friction, because the wheels are sliding. So instead, I started driving before anti-lock brakes were widely distributed in cars. So we were taught to, if you feel the car sliding, you've got to let up on the brake, and then you can apply it again, and you would actually pump the brakes, you'd call it. So a little bit on, a little bit off, little on, little off, little off, back and forth. Anti-lock braking systems are electronics. They do that, I don't know, hundreds of times a second. Keep going like this. Because they want to make use of this maximum static friction, which is always greater than the kinetic friction. When something's rolling, think about that. If something's rolling here, there's only one point of contact between the wheel and the surface. And as this is rolling, it's a new point. So this wheel operates only with static friction. That's how it transfers force from your car into the ground or vice versa. We want to make use of that movement and not sliding to maximize our slowing power, because the static friction is always bigger. So if you get into a slide, you're going to slow worse than if you can keep the wheels rolling. And that's just a function of this. It's an application of this static friction. So Yeah, I guess that's the main thing. When you guys plotted friction versus normal force on that lab, what'd you get? Slope. You got a line, right? We're pretty close to a line. And I saw one or two that were a little curved, but most of them I saw were lines, which means that the y variable is proportional to the x variable by some constant. And we abbreviate that with another little mu. That's the same form as kinetic friction, which was mu k, kinetic coefficient of friction, times the normal force. So these have the same sort of forms. It just so happens that mu s is always greater than mu k for that reason that we were talking about. If it was not, once something started sliding, mu k would stop it instantly. And then we'd be back here. So we couldn't really get things sliding at any point. So that relationship is always true. There was another part of this that I thought was interesting, and I redid it shortly after you guys were kind of done with data because I wanted to double check that everything was working out. Some people had a pretty linear variation with their angles, so that as you increased the mass, it kept going up. I think one group had that it kept going down. And so I double checked. And what I found was that whether I had a heavy block or a light block, there was 1 or 2 degrees difference each time. It was almost the exact same from maximum mass to minimum mass. And there is a reason for that. On the fronts of our that lab sheet, we wrote 2 sum of the forces equations for our for x and 1 for y. So in the x here, we had a force of gravity going down the slope, which we determined would be the weight of the object times the sine of the angle, because that was a component actually in that direction. And then we had friction going the other direction to keep it steady. And since we were looking for the maximum friction, we said, well, it's not really going to accelerate at all. We're looking for that breaking point. And then we looked for the y dimension. We said, well, the only 2 things going in that dimension are a normal force and the mg cosine theta, the portion of the weight going directly into the ramp. That's always equal to ma, but again, it's not going to leap off the ramp or suddenly sink into it. So those 2 things are true. But now let's look at it. Our graphs, I can't make this go up. Our graph gave us that static friction is equal to that coefficient, mu k, times the normal force. I want to actually get that in terms that are not directly related to the mass that's in place and that sort of thing. I want to explore this relationship. For this, we said that we've got, sorry, I'll start over. I don't have to start over, I'll just re-explain this. If we solve this for normal force, I can put it in there. So since that's equal to 0, we can say that, all right, normal force must be equal to that mg cosine theta, the amount of gravity going directly into the ramp. I'm going to take that and put it down for my normal force. Likewise up here, since these 2 are equal, the difference between those 2 are equal to 0, that must mean that my static friction is equal to the mg sine theta. I'm going to take that and put it in for my static friction. So the formula of my line becomes mg times sine of theta is equal to that mu k times the mg cosine theta What can we do with that? Erase mg, because they're on this. It's on the same side. If we divide through by mg both sides, we get rid of those. I'm also going to divide both sides by this cosine theta, which means sine theta over cosine theta is equal to the mu k. What's that? Tangent. What this says is that that static coefficient of friction doesn't depend at all on the mass of the object. It only really depends on, or at least we can find it based on the angle of our ramp. And it should be the same every single time, irrespective of mass. It only depends on the angle that we find when we tilt that, the angle that it starts sliding. So essentially, what we're finding, it makes sense if you were finding these that it doesn't. And several groups found that the angle didn't. It kind of went up and down, or at least it didn't change consistently. This is why, because if we measure really, really carefully, and certainly, one of us holding it up probably doesn't meet that really, really carefully criteria, then what we find is that angle would be the same for any mass, assuming the two surfaces are the same, so the wood block on the aluminum or whatever. Okay. The rest of our time is on the homework problem set, which is in the book. For all of those problems, some of them will be very simple actually too. But for all those problems, practice the method that we're going to use even when we get to more complicated problems, which is draw a representation of the object that you're interested in, draw out the free body diagram with any forces acting on it, and then use those to write out the sum of the forces equations in each direction. And remember, whatever you're adding up in here, whatever the different forces are, what are they always equal to? What's that?
GA, like mass, gravity, times acceleration.
You don't close. Mass times acceleration. Mass times acceleration in that direction, which might be 0 if it's not accelerating. If you know that it's not accelerating, it's okay to cross that out and put 0. But sometimes you won't know. Sometimes you'll have to find that acceleration. So you'd leave it like that. Okay.